Yeah, so I was kind of working on that because one of the big projects that the Army Corps wants to do, in all right, folks, thank you so much for joining us today. My name is Brooke Blosser. I'm the Science Outreach and Communications Coordinator here at the Marine Resources Council. I see some familiar faces in the audience. I also see some new faces in the audience. Either way, we are very glad to have you here at the Lagoon House today. For those of you that are not familiar with the Marine Resources Council, we are an environmental nonprofit focused on protecting and preserving the Indian River Lagoon, which just so happens to be right there. Once a month, we do Lagoon at Noon talks where we have speakers and scientists and nonprofit leaders and different leaders within our environmental community come and talk about a subject related to the Indian River Lagoon in some capacity. We are very excited to have you all here today. And before I introduce the speaker, I want to go over a couple of housekeeping things. If you have phones on you, please go ahead and silence those phones for the presentation. If you are in person, I have passed around note cards and pens to everybody. We will ask that you hold your questions until the end of the presentation. If you are online, there's a chat box enabled. You can put your questions in the chat box at any time. Once the presentation is over, if you are in person, you've written your questions on your note card, I will come around and collect those, and then I will ask the questions. We do this just so that people on Zoom can hear the questions that are asked. I also want to let you all know that we have a couple of volunteer events coming up this month in February. If you are interested in joining us, we have our first Friday Litter Sweep this Friday at the Lagoon House. I believe from 8:30 to 11:30. We also have a Palm Bay Mangrove Workshop coming up the following Friday. And very, very exciting news that I am thrilled to announce today is that we have a beginner birding workshop that coincides with the Cornell Great Backyard Bird Count weekend. So if you have thought about getting interested in birding or want to learn more about the event, come talk to me and I'm happy to point you to the link to register. We do have some limited spots remaining for that. We want to get a full house because we'll have an ornithologist here to give a presentation, much like this, and you guys will have an opportunity to contribute to the Great Backyard Bird Count, which is one of the largest citizen science projects probably in the world, but definitely with birds. Without further ado, I will present our speaker today, Dr. Lauren Schambach. She is a coastal modeler, PhD in ocean scientist. She is going to present on coastal modeling, which I always like to tell folks. My background is in marine science, and if there is one class that I could have taken and never done marine science ever again, it would probably be a coastal modeling class. This is because I live at the beach. And if you live at the beach or live anywhere surrounded by water, this is an absolutely critical lecture to listen to. So I'm really excited for this speaker, and I hope you guys are too. Without further ado, let's give our speaker a hand.
Hey y'all, thanks for inviting me. As Brooke said, my name is Lauren Schambach, and today I'm going to be talking about using models to understand our coast. And basically, this will be like a little coastal modeling 101. And my clicker is not working, so
Try again.
there we go. Okay, so a little bit about me. So I was born and raised at the Jersey Shore. I spent 10 years in Rhode Island for school and work. I went to the University of Rhode Island for a bachelor's, master's, and PhD in ocean engineering. They couldn't get rid of me. I also had a couple different places that I've worked in industry, and for the last 2 years, I've been working as a coastal scientist for a company called Deltaris USA. Deltaris USA is a not-for-profit organization that does a lot of research in water systems and modeling, as well as we work with our partners at Deltaris, which is a research institute in the Netherlands. And they create a lot of open source software. So that's software that is free to use and that you can actually go through the source code and see what exactly equations are being solved. And that's a way that we kind of give to our community and help progress the coastal sciences. I spent 2 years in Boston after being in Rhode Island, and now I live in Indialantic. I've been here for about a year and a half, and so far so good. It's really lovely down here. Okay, So this will kind of be like coastal numerical modeling 101. And that might sound a little bit intimidating, but I'll try to break things down in concepts that everybody here can understand. So first I'll talk about like what is a physics-based numerical model? What does that mean? And then how do we build them? So I'll talk about some of the typical ingredients that go into a model. I'll talk about setting up a model like mesh generation, bathymetry and topography, which is elevation data, forcing and boundary conditions. I'll explain what that means. We'll talk about executing a model. So you can do it like locally on a laptop. There's also high performance computing you can use, cloud-based computing. I'll touch briefly on that. We'll talk about some post-processing results and some example applications for how you would use the results that come out of these models. Okay, so starting off, what is a physics-based numerical model? So there's a lot of different words on here, and I'll try to break down all the different pieces. So a physics-based numerical model is a computational algorithm that solves equations derived from physics. So there's a couple different conservation laws in physics that we can basically create equations that describe these laws. So the main ones for hydrodynamics, we aim to solve for fluid motion by doing conservation of mass, conservation of momentum, conservation of energy. Models are differentiated by the specific equations that they're solving. So we can kind of have this full picture of the different equations, but there's different assumptions that can be made to simplify those equations. And the model that you're using basically depends on how you simplify those equations and then how you solve them on a computer. So in coastal modeling, there's lots of models to choose from depending on what you're trying to do. There's a whole list here, for example, Del3D, Sphinx, XP, Swan, FunWave, NHWave, STWave, WaveWatch 3, List Flood, Mike 21, AdCirc, Schism, FECom. There are so many different kind of models. And the way that they're differentiated, like I said, is based on what exact equations that you're solving and how the model actually does that internally. Okay, so the equations that we're solving, these are called governing equations. They're equations that basically describe how you're going to let the fluid move inside your numerical domain. So a couple different examples of these types of flavors of models that I just mentioned. You could have a circulation model. These are kind of like big, large-scale tidal models that could maybe cover the entire ocean basin. Or maybe you're looking at a circulation model in the lagoon, for example, and you're interested in kind of the more detailed processes going on locally. You have wave models. So for surfers, a lot of times they want to know, hey, like, what's the wave forecast going to be? They would use a wave model. Those models solve for things like wave heights, period, direction, associated velocities of the waves, sometimes wave setup, braking, those types of things. We also have sediment transport models. So this would be important, for example, if you were looking to figure out a beach renourishment project and say you put a bunch of sand somewhere and then all of a sudden a storm came and all the sand disappeared. You could use something like a sediment transport model to help you figure out where that sand went. We have coupled models. So sometimes you want to know about all of these different processes. And what you could do is you could couple them all together in different ways. Okay, cool. All right, so I will give a couple examples throughout this talk, and some of the examples relate specifically to the Sphinx model. So Sphinx stands for super fast inundation of coasts. It's designed to very quickly be able to calculate some compound flooding in a specific area. So this is kind of an example flood map that would come out of the model when you run a situation. So what I mean by compound flooding, that's an event that results from many different things happening at the same time that you take account for in the model. Historically, sometimes we may have done models of tides and storm surge separate from a river discharge coming in or something like that, or maybe we wouldn't take rainfall into account. And when you model those separately and then add them together, sometimes the results look different than if you add all of them into the same model. So coastal compound flood model allows you to kind of take all of those different things into account. Okay, so briefly kind of explaining the way that we're going to solve for conservation of mass and momentum and energy. We kind of usually don't do the conservation of energy in the equations that we typically are solving. It's usually mass and momentum. But what I'll have you do is I'll have you picture this cube here, and it's filled to a certain level with water. And if I start putting allowing water to enter the cube, for example, from this edge right here, what do we think is gonna happen? Yeah, the water's gonna go up, right? So, because I'm not letting the water leave. So if you're adding water in, the water level is gonna go up. Now say I added another cube to it and I opened this wall here and I'm gonna let the water go in between these two cubes and I'm still adding some water in this way. What's gonna happen?
The water's gonna spread.
Yeah, the water's gonna start spreading into the next cube over, right? Okay, say I add another level to this, so where our water's kind of coming in, it's flowing inwards. And say I put a bunch of like really tall seagrass at the bottom of these two ones. Do we think the water is going to flow into those slower or faster because all the seagrass is there? Slower, right? All right, so that's kind of the effect of like bottom friction, which we put in when we have like seagrasses or mangroves or something like that. Usually it allows the water to kind of slow down and it slows that process down instead of having a sandy bottom where the water would be able to flow in a lot more quickly. Okay, so we kind of showed that going in one direction, but we can do this in 2D as well, right? So we can add multiple dimensions. We can even get really complex and have 3D models. So you're solving for the what's going on in the water depth, as well as if you were kind of looking at a map. I'm mostly going to be talking about like 2D models today. Do we just think kind of like in 2D and we don't really worry as much about the depth? Okay, so if this is our model setup and there's kind of 6 cubes here and the water can't leave the cube. And say at this boundary, I'm going to start forcing the water level to go up and down in the kind of sinusoidal motion, like sort of like a tide, where water goes up, it peaks, starts coming down, it peaks at the bottom, and then comes back up. So if I'm forcing at this boundary, I would be applying a forcing, and that would be my boundary condition. So it's a condition that you're imposing on one boundary, and I'm not going to let the water leave the domain. So when I increase the water level, so this is coming forward in time, so we're going to increase the water level. The water is kind of going to go up here. The next cells over are going to say, oh, hey, there's more water in that one. It's going to start flowing into the subsequent cells. Once it reaches the peak, the water is going to continue raising in those other 2 cells. But then all of a sudden, the boundary condition is saying that the water level is going to lower a little bit now here. These cells don't really know that yet. They're still rising. And so they're still kind of coming up and then cresting, and then they're going to start following that pattern, right, of going back down. And so as we step through time, we can see kind of how those boxes are going to move. And so that's kind of like the concept of what we're solving. We're not letting water leave the domain, and kind of motion that you're imposing needs to be taken into account for in between the different cells. So for anyone who's a little bit more technical, these are the governing equations that are in Sphinx. So this is the conservation of momentum equation. We don't have to worry about this specific equation, but I'll tell you some of the things that are in it. So what we're doing is we're looking for the flow rate at the new time step. So this is the flow rate in between the different boxes. So those are going to depend on things like the flow rate at the previous time step. So what was it previously? The water depth, gravity, a roughness. So that was kind of like that seagrass that we talked about. The water level gradient. So what the water is like, is it tilted in between the 2 boxes? That's going to cause some fluid to flow that way. There's some additional forcing terms, which we'll talk about shortly. And then the time step. So over which time period are you kind of doing this? Similarly, we have the conservation of mass equation or continuity equation. These are basically the water level in a grid cell. That depends on the flow rate at the different cell phases, and then any source or sink term. So if you add water to the system, for example, rainfall would be an example of adding water, or a river discharge, for example, you'd be adding water at a specific point where you have a river coming into your coastal area. Okay, so this is an example animation of a Sphinx model of Hurricane Ian. This is the west coast of Florida. Fort Myers is located here. The hurricane is going to come from this area, and you're going to see the little white dots here are going to kind of be the wind speed, and then the colors you're going to see is the water elevation in that particular area. So hopefully this works.
I have
Yeah,
to
can you?
right.
Yeah, perfect. All right. And we'll see if that can just play one more time. I don't know if it'll on. Yeah, there it goes. All right, so we see kind of the wind fields and the pressure field kind of come over the model domain area. The area we're solving at is this kind of all the area covered in blue. And you see how once the winds kind of like enter this specific area, the strong winds and the pressure, they're creating an increase in the water elevation. And so one of the things that we do when we run models like this, we usually like to look at historical cases where we have some observational data. So on the bottom here, at this Fort Myers location, there's a tide gauge that was taking observations of the water levels as they were happening. So something we do when we make a model is that we'll compare what the model is saying the water levels would look like, and we make a comparison against the observations. When the comparisons match, we feel that we have accurately created a model of this particular situation. Sometimes they don't match. And what that means is that maybe we are taking or making an assumption that doesn't work for this particular case. We need to maybe look at our input data and make some changes to what we're inputting into the model. Maybe we need to look at the elevation data stuff that we put in. Maybe there's something going on there. So we would do some investigation into, oh, like why are we not kind of getting the results that we're expecting? Okay, now we'll move on to some typical model ingredients. So the starting point is always the region that you want to model, right? You have to decide, hey, am I modeling the entire Atlantic Ocean? Am I modeling just India Atlantic? Am I modeling the whole Indian River? So basically, the region that you want to model is going to help dictate, what you're going to pick for a model. So you're going to pick kind of a large scale circulation model, and you want to do things like tides. Are you looking at something that's way more local? Like you want to look at the influence of the waves on a particular beach, and how that influences the sand in like one small area. So all of these things kind of lead into you deciding what model is most appropriate for what you're trying to do. So the region that you want to model is important. So then the things that you absolutely need to run a model is information on the elevation. So this is the bathymetry and topography. So this is kind of the elevation map of the area that you're looking at. The other thing that you need is some sort of model forcing. So that can look like you have information about the offshore water levels, kind of like I showed. And so you're going to impose a tidal signal, and that tide is going to kind of flow into your model domain. River discharges is another example of the model forcing. Wind and atmospheric pressure. So with hurricanes, those are main causes of storm surge. And so you would use wind fields and pressure fields kind of as your input here. So those are the things that you need. You need your area, the elevation data there, and some sort of model forcing. If you don't have any model forcing, you're just going to have flat water and nothing's going to happen. So there's some other optional things that you could put in. So information on land cover, this would be like the roughness. So if you have mangroves or seagrass, or you have big boulders, or you have, flat sand, or maybe it's concrete, all of that is going to influence how fast water can flow in and out of certain regions. So land cover kind of correlates to this roughness idea. Information on soil type, if you're doing something like wanting to know how the precipitation is affecting things. So if you have no infiltration, that means that all the water that falls from the sky is going to stay on the ground. If you have infiltration, that means that some amount of that water is going to be able to seep into the ground and kind of leave your system. Any information about local structures. So sometimes you have jetties or levees, or you have water pumps, for example, that are kind of pumping water in and out of different locations. So those are different things you can also parameterize and add it to your model. Okay. So I'll go a little bit more into showing you what I mean by these different data sources. So elevation data. So what you're going to end up with is something like a model grid, and it's describing, okay, like here's where it's water, here's where it's land. The elevation is kind of going like this in the area. There's different resolutions of this data that you can find if you look for some of it online. There's this concept of resolution. So this is how much information is known about a certain area. So if I was looking at just the little box around me, that's a pretty small resolution, but I can also consider a box that is the size of this entire room. That's a much coarser resolution. So obviously higher resolution gives you a lot more information. That also makes it really expensive computationally. If you have a lot of little boxes you're solving against, you're going to have to solve all these equations across all of them. You can imagine that gets pretty intense pretty quickly. So for example, this is kind of the area I grew up in. This side here is a really low resolution data set that covers the entire globe. So in a lot of cases, that might be fine. If you're just generally interested in some offshore tides and you don't really care what's happening inside the land, that could be okay. But if you want to do something detailed kind of in these estuaries or something like that, you're going to need a really higher resolution data set underlying your model. So where do we get this information from? So in the United States, the NOAA Digital Coast Data Access Viewer is a great resource for all of the different types of bathymetry data sets. So I just drew a box around the general area we're in right now. And there were 31 results that popped up of different bathymetry sets covering different areas of our region where we are right now. Oops. So some of these, for example, we have Tabubathi LiDAR post-Hurricane Milton. And then there's some that happened previous to that. And so what you could maybe do with those two different data sets is run a simulation of the hurricane and say, okay, if I use a pre-Milton bathymetry set and then run a simulation and then compare whatever the result is to a post-bathymetry data set, then give you an idea if your model is working well or not. So this is why it's important for us as coastal modelers who are investigating these things to not just have one data set, because our coastlines change a lot, especially, over 20 years. If you don't have a data set in between two 20-year periods, then you might not be able to model something very specific to your specific beach, for example. Some of the ways that this used to be done are just surveys on the ground. What's done commonly now is we fly LiDAR, which is from planes. And so it's light detecting and ranging. There's some algorithms that they use to kind of give you back a map of the topography in the area. Yeah. So USGS also has some high resolution data sets. So NOAA is usually typically good for the bathymetry data sets. Sometimes the data comes from USGS when it's more the United States Geological Survey, when it's more kind of in the inland areas. Sometimes your model is going to go in between the two, so you kind of maybe would look for data from different sources. But typically between these two in the United States, like you'll find some really good data sets for your specific area. Okay, so if I have my elevation data, next I want to create my computational mesh. So some of the important things for this, for a basic mesh, are these kind of typical inputs. So you need some way to locate your mesh in space. So an X and Y coordinate in space. This could be latitude, longitude if you're doing a large model. A lot of times for local models, we're working in feet or meters and measure things that way. So for example, here, I'm specifying the lower left corner X and Y coordinate of this particular area. So it's just kind of this area to the southwest of Miami is where I kind of want my mesh, my model grid to start. You also need to give information about the width of the grid cell in the X direction and Y direction. So each of these cells has a width called dx and a height called dy. And so with that information, and then the number of grid cells that you want in the X and Y directions, you basically have described a grid. And you could also add something like rotation in if you want to have your grid rotated. In this particular case, I increased the dy here. And so basically these are things that are utilized internally to the model, along with your elevation information, to be able to solve what's going on between the grid boxes, like we showed earlier. There's a whole different world of different types of meshes that you can create depending on the model that you're using. Some of them require you to have this kind of like a box, and that's what you need to do. There are other models that let you use different types of elements because of the way that they're written and they solve things. That they don't necessarily need to be boxes, or they could get bigger and smaller. Some can use triangles of different sizes. So you can have increased resolution where you want it and decreased resolution in areas that you don't care as much about. Okay, so yeah, like I said, so after you create your model mesh and you have your topography file, there's some processes where you basically put the topography information onto your mesh. And that is one of the most important pieces of a coastal model. Pretty much, I would say in my experience, the majority of the time that I see a result that doesn't look like something that was observed, it's because I have something wrong in my bathymetry. Sometimes you have to look at it and the data set that you have, instead of it being a bridge, they thought the bridge was actually a land mass. And so that land mass is kind of in your model. And you'll need to figure out a way to carve that out in some aspects. So it's important to have some local knowledge too about the area that you're modeling, so that when you're looking at that, you say, oh, okay, you know, this is why this isn't working. Okay, this is maybe a little bit too complex here, or too in detail. But there could be different coordinate systems and vertical datums that these elevation data sets come in. So that can also be a source of error if you're not paying attention to these things. So a lot of times we want to make a local model where we would look at something in feet and meters, but some of our data set grids come in latitude, longitude, because the Earth is a sphere. So there's different projections or way of taking that spherical data and making it a flat map. And there's tons of ways that people can do this. And so when you're building your model, if you're using one that used one projection and combining that with something that used a different projection, and you didn't take that into account, you can get some really funky results. Similarly, there's lots of different tidal datums for coastal data that we need to pay attention to. You can imagine if you're in kind of an inlet area or somewhere where there's a lot of shipping, a lot of your information is going to be with respect to the lowest water levels. Because who cares about the lowest water levels? People who are on ships, right? Because you need to take into account the draft of your ship. You want to make sure that you're not going to crash it. So usually a lot of those maps are referenced to that really low water level. But if you're someone who wants to model flooding, you're not interested in that super low water level. You want to know what the highest water level is that's being experienced in these areas. So those are called vertical datums. And so they can be related to a tide. And you need to make sure that when you're looking at different data sets, that you are taking that into account. So you're not taking one where it says, hey, this area of my grid, I'm going to say with this low water level, and this area is combined with something with a high water level. There's going to be this huge mismatch at the line where those two things connect. So that was a lot about topography and bathymetry, elevation data sets. But I want to stress that when you're building one of these models, that is like one of the most important parts. Okay, so next we're going to talk about a little bit about the forcing data. So now I have an area where it's like, this is land, this is water. My water's just laying flat there. So I want to do something interesting to it so the water moves. So how do we do that? We have to put that boundary condition on, where we're going to tell it how that offshore boundary is going to move. So whether it's going to be from a tide, whether it's just going to be flat and we're going to blow wind over it and that wind is going to move the water around, something like that. So again, in the US, NOAA is a huge resource for some of the different models, offshore models that we can connect our coastal models to. There's also several tide models where you basically have different tidal constituents. And and the different tidal constituents, and be used to kind of describe what the water level is doing at your offshore boundary. Okay, so in this particular example, like we're going through the process of making a really basic Sphinx model. And so I have my grid, I put my topography on it. The next thing I want to do is actually say that I'm going to let the model know what is happening at this offshore boundary that's highlighted in red. So basically, at every single grid point along that offshore boundary, I'm going to give it some information about the tide and how the water's moving. So the model knows how to propagate that information towards the coast. And then we can take a look at the effect on the flooding there. Okay, so the way that this does this is that you define some boundary points where I'm going to give this signal as the input. So this is exactly kind of what we looked at earlier, where you're giving a signal that looks like a tide, and it's going to come in at all of the edges of this boundary, and the water is going to move. Okay. Some other forcing information and data that we could put in. If you're in an area where you have a river that's kind of feeding into your coastal area, sometimes you'll have really high river discharges, and that affects the total water levels in your area. So again, NOAA and the USGS have some really great data sources on some observations. They also have model data that explains kind of how those different things work. Okay, meteorological data. So this is like wind, atmospheric pressure, precipitation. I don't know if you've ever seen this website called Windy. I would recommend going to, it's called windy.com. They have really nice visualizations of the wind data, pressure data, rain data, and the place that they're getting all of the underlying data for their maps from are these different models here. So you can choose which model you want to visualize on this particular app. So I'll talk a little bit about some of each of these models. So some of the ones that they use are ECMWF, that's the European model. So basically they're taking the outputs of the big European model and they're just displaying it for you. And so that happens for a lot of these different apps that we use. They're actually taking the data from one of these models that are run by either the Europeans, or we have our United States national models that they're pulling these data from and they're visualizing it for you, which is really cool. Yeah, again, GFS, the Global Forecast System, North American Mesoscale Forecast System, the High Resolution Rapid Refresh. These are all different types of NOAA wind and atmospheric data products. They have different resolutions. So, you know, the one you want to use depends on what exactly you're doing. And some work better in some areas than others. So you'd have to do some tests on, okay, like let's use this wind product, run our hurricane simulation. Does one do better than the other? That's something that we'll look at a lot. Okay. So we kind of have created our model at this point. And what our model is, if you're looking at it on the computer, is a bunch of text files with weird extensions. This could be intimidating for someone if they don't, they're not familiar with it, which is totally understandable. But most of the time, if you right click on these and open it with a notepad or note editor, what you'll see is it's just a bunch of keywords and numbers. And I'm sorry, this like screen isn't really great resolution here. But they're just a bunch of keywords and numbers. And those are things that are describing your simulation. Like for example, I have a T-start, T-stop, and that's, says like 2025, 09/31 or something like that. So I'm running September 30th, 2025. That's my start time, and my stop time is a week later or something like that, right? So you're basically telling it this is when the model starts, this is when the model stops. From that, the model knows how long it needs to simulate. Some other things that are in this input are things like the roughness, if you want a constant roughness over your whole area, or you would give a file with like the variable roughness over a map. And then you also have a couple of files that are describing your inputs. So one of these is this boundary point file, and all it is an XY coordinate of these different points where I'm saying I'm gonna give you the information of what the water level is doing. So then if you look at the file that correlates with that, it's basically this tidal signal, but written in text. So the first column here is time. And so that's the time along this axis here. And the next column is the elevation. So it's gonna go, okay, for each time, here's my elevation. And as it steps through time, it's gonna pick up the new elevation at your offshore boundary. Cool. You can also add some observation points. Again, if you look at the file, it's just X point, Y point, and then a name for the file. So when you actually open these files and start looking into them, they're less complex than maybe they would seem if you weren't really sure what you were looking at. Cool. So then we can run the model. So basically when you look at Sphinx, which I'm using in this example, I have a folder that has all the Sphinx related files in it. These are a bunch of libraries that are needed, and there's this sphinx.exe. That's like double clicking on Microsoft Word and Microsoft Word pops up. I would double click on sphinx.exe and the program pops up and it'll read my input files, run the simulation, and create some output files. Cool, so I could do that on my laptop, or I could send that off to a supercomputer. So the way that you would do that is you would basically take all your input files, put them in a folder, kind of send that over the internet into a folder where you have an account on a supercomputer, and you tell the supercomputer, hey, here's my input files, here's my Sphinx file, you run the simulation, use all these cores that you have available, your simulation is going to run a lot faster than if you did it just on your laptop. It's very similar for cloud-based computing. Basically, we think like, oh, we're running in the cloud, but the cloud is really just a set of computers, right, that these different companies have. So what you're doing is essentially putting your input files over there, putting the software over there, telling them to run it, and then you'll pull the results back and look at it. So when you have huge models, or maybe you're running something for a really long time period, it's typically customary to run those on these high performance computers because it'll make your laptop not work for like weeks sometimes, depending on what you're trying to do. So if you need your laptop or your desktop for other things, it's probably best to send that somewhere else to run. Okay, cool. So first processing results. So this is the output that came out of the model. This was my input, and you see that they pretty much match, right? We would expect that. If I'm telling the model, hey, at this point right on this edge, I want you to do this signal, and I want you to give me the output pretty much right next to it, you would expect to see basically the same thing. And then there's another point that I put that's located just here. And it's a little hard to see on this screen, but the water level is slightly delayed behind this first one here. And so you could imagine that it took the tidal signal a little bit longer to reach that particular point. This isn't like the best demonstration example, but you can kind of see it. Okay, cool. So this is our basic simulation that I made, and we saw some of the input files for, and this is an animation of the output. I think you might have to click that. Yeah. Okay. So I was saying, hey, at this offshore edge, we're gonna vary the water levels up and down. One of the things you might notice is that there's nothing really happening in this area. Does anyone have any idea why?
Elevation?
Elevation, exactly. Is that what you were gonna say? Yeah. So I made a really, really coarse model because I wanted an example that would run really fast on my laptop and I didn't want it to take forever to run. And if you'll notice, I don't really have any water being able to enter this area because it's all green here, which is land. So if the water can't flow into that area, nothing's gonna happen. So with that in mind, what is something that we could do to this model to make it work a little bit better?
You could increase the amplitude of your input.
I can increase the amplitude of my input. So basically what that might do is it might give water levels that are high enough that it could go over kind of these barriered areas that I have, right? That might not be realistic though. What if you don't get super high water levels in this area? And if you're imposing those, then that might not work.
Proper data.
Put in what? Sorry.
Proper data.
Put in the proper data. So this is the actual elevation. What's wrong with it?
Oh.
It's too coarse, right? It's definitely not detailed enough. So what I could do back when I was creating the model over here, back when I was creating the model, what I could do is I could make this dx and dy smaller. So all your grid spaces are much smaller, right? And then pull in that topography information, and then you'd have a lot more detailed model. So spoiler alert, I did not do that. But if I did, we would probably see in that particular area, you would start getting water levels kind of coming in and out of that area that was blocked off. All right, cool. So yeah, doing okay on time, right? You're good. Okay, nice. So I have just a couple example applications of like, what would you do? You know, you say you ran this model and you have a map of the flooding that happened during a specific simulation. And the map looks like this, and like, but now what? So the running of the models and that type of stuff is typically where my job as a coastal modeler would end. But that's where the next part of the process begins. So a lot of times we're giving these maps to people who are planners, or they're working on the flood insurance rate maps. Like I don't particularly do that, but there would be, you know, there's a team of people who run these coastal models, come up with maps, and then they can set different rates and stuff based on that. Planners could be like, oh, hey, is this a good area to build? And you can put in ordinances to say, hey, we should or shouldn't build here. There's different, for example, there's different wetland areas here that maybe people would want to develop on. But when you run a model, it shows that that's actually really important for blocking some of the flooding from areas that already exist. So you can imagine that that might be interesting to know about. There a lot of times people want to put in some sort of structure. For example, seawalls are really common things that people say, oh, well, like we just want to protect this area with a seawall. So what we could use these models for is to do hypothetical scenarios where we would put a seawall in the model that doesn't exist in real life, and you can see how that changes where the water flows. So that's something that we might use it for. This is an example in Charleston, where we took some flooding information and overlaid information about different buildings. And we had some information from a national data set, kind of the estimated cost of the damages that those different floodings would cause. And you can create different heat maps showing like, hey, in this particular simulation of this hurricane, these are the areas that we saw that were really heavily impacted. We can run simulations of events that actually happened or hypothetical events that could happen. In this particular case, you can look at, there was a hurricane that passed there that was about 60 miles off from being a direct hit, but they pretty much evacuated a lot of the area of the city. And then what actually happened wasn't that bad. And so people were upset because they were like, why did you make me evacuate? But the thing is, if you ran a simulation where you just slightly shifted that hurricane, you would see a totally different picture. And so it's really important for also outreach activities for cities and emergency managers to be able to explain to people why they made the decisions that they made. Because in the end, all they were trying to do is to keep people safe, right? So those are some of the applications that you might use this for. Another thing could be planning out evacuations or checking out people's accessibility to hospitals or something like that. So you could basically take simulations and simulate the water kind of coming in, how much time it takes, what roads get blocked. And then you could say, hey, this neighborhood here, actually, if this event happens, they would not be able to access whatever emergency service you might be looking at, or they might not be able to evacuate away from the beach, right? We can also use these models to train AI. for example, artificial intelligence is something that everyone is talking about. I'm not an artificial intelligence person. I prefer the physics-based models, but what they're using this for is they're doing a bunch of different simulations of a bunch of different things using the physics-based numerical models, and they're using that to train the AI to be able to do different applications. So that's also an application for where someone might want to use one of these models. And there are tons of other things too. So that's what I have for the presentation. I think there's plenty of time for questions, and hopefully you guys learned at least something. Thank you.
All right, folks, I'm gonna come around and collect your question cards. If you are online, please put your questions in the chat and I'll go ahead and open that up. If you have a question card, go ahead and hold it up that way. But perfect. Thank you. Thank you. Thank you. Thank you.
We didn't get one, did we have one?
I'm sorry?
No, sorry.
Fix that guy.
All right, we'll go ahead and get started today. So our first question relates to the end of your presentation.
Yeah.
About artificial intelligence. And how are these processes improving efficiency in the field, and in what ways is it being used?
The artificial intelligence. Okay, so I'm not going to be able to fully answer that because, like I said, I'm not working on that part of things. So I work on just the physics-based numerical models, and I'm kind of in that area. But from my understanding is that we have a lot of these different models, like I said, right, that are solving different equations that are accounting for different things. And there's a lot of these running operationally. There's lots of data that's being output from them. And so something that AI can do that a human person couldn't is maybe look at all of these different outputs and find ways that they might be interrelated that a person might not see. Again, I don't know a lot about AI. I just know that the inputs and outputs kind of that we are creating with some of our models are being used to do different applications with that. So.
Great question. And I will also follow up with my own personal question on that, which is, I think a lot of people are thinking that AI is the next, big thing, and we're really excited about it. On the other end of that, what is an aspect of your job that you think AI cannot replace?
So there's a lot of things, right? So if you're going to use our models to train your AI, if our models don't exist or our models don't continue to get better, the AI won't be able to just magically get better. Also with AI, you need data collection to keep happening, right? To stay up to date with kind of what the coasts look like, what the sand's doing, and those types of things. So it could be a super useful tool, but I think we need to look at these as all things that are working together. Like you still need people to go out into the field and collect their field data. You still need modelers to kind of be looking at the physics, looking at the algorithms, figuring out how we're solving these different things. And then you need the people who are working on AI and machine learning algorithms to understand kind of where that data is coming from, be able to ingest it, and be able to show different things. So I think it's very exciting. You see some things and you're like, whoa, this is like magic. But I think it's important to keep in mind that you need all of the pieces. You can't just say, well, AI is going to do it. We don't need people who understand this anymore, because I think it's important to have people who understand kind of how these things are working personally. So yeah.
Good. Thank you for that. The next question kind of relates to the beginning of the presentation, but can you explain a little bit more about why the conservation of mass and momentum is important specifically to coastal modeling?
Yeah, so the conservation of mass and momentum is the governing equations of how the fluid's going to move. So if you don't have those equations, the model doesn't have anything to solve. So if I go back and show maybe
Try again.
Go back to the beginning here. Can you find the slide that has the equations on it?
Yes.
All the way, yeah, those two.
Okay.
Yeah, okay. So this is the conservation of momentum equation that's being solved in the model. So the full conservation of momentum equation is super long. It has a whole bunch of different terms. And then we'll make assumptions about our specific model that we're doing. And that allows us to kind of cut some of those terms out, make it easier for us to write computer codes that can solve the equations here. So one of the assumptions that we made in this particular model is that we can depth average. So we actually don't care what's going on at the bottom of the ocean and what's going on at the top of the ocean. Those might in real life be different things happening, but we average what's going on. That's an assumption we made that takes out a whole bunch of terms. This equation would just keep going if we don't make that kind of assumption. Another assumption that we make, for example, is that we typically say that water is incompressible. So if I had a cube that was filled with water and then you start pushing on the different sides, water being incompressible means that you actually can't compress it anymore. Air, for example, a box of air, you could say you had like a water bottle filled with air on an airplane and you kind of put the cap on, you go up in the plane and the bottle expands, right? Because the pressure inside changes. Or if you kind of squeeze the bottle, you can squeeze the bottle some and it'll crumple, but no air came in or out of the bottle, right? So air is more compressible. So we assume that water is incompressible, so you actually can't smush it any more than it already is. And what that does is that gets sort of a whole bunch of terms as well. In real life, you can a little bit squeeze it, but we usually say the effect of that does not have any effect in what we're trying to solve here. So those are the types of things when I say we're making assumptions, it's really so we can simplify these equations a lot more, and different models simplify different parts because they care about different processes. So hopefully that sort of answers the question.
That was
But these are the two main equations, right? And they come from physics, and so you'll have a whole bunch of terms that say, basically things can't come in or out of the system unless you tell it to, and motion going on in one cell is probably going to affect the next cell, that type of thing.
Ocean physics is a really fun course. So lots of different things lots of different assumptions that you have to make when it comes to ocean physics, which is always lots of fun. So you did talk a little bit about the computer. If you were to run one of these models on your laptop, it might take weeks. Alternatively, if you were to send one of these models to a supercomputer, how long would it take for that to run a model?
Okay, so all of this totally depends. If you have a really coarse resolution, kind of like the one I showed at the end, you can run that on your laptop, like 1 second for the Sphinx model. The Sphinx model is designed to be really, really fast. If I increase the resolution of that a bunch and ran the same simulation on my laptop, it would probably take a couple more seconds, because for that example, it's a really, really fast model. Some of these other models are really computationally heavy. You're typically looking at a much bigger area. So if I wanted to run something on my laptop, we're talking like 5 hours for a really basic computation. If I send that to a supercomputer and have access to a lot of different compute nodes that can all talk to each other and run parts of the simulation at the same time spread across them, your simulation can go from hours to minutes or days to hours. And it really depends, how long are you simulating? What is your resolution? What model are you using? And how many like equations is it solving? So these are, this is more basic, but sometimes for some models, we don't make all those assumptions, we keep them in. And so the computations would take a lot longer. So I would say it depends, but we're looking at like, typically on a laptop or a desktop, your simulation is going to take hours to days. For the same models on a supercomputer, it would take, more like minutes to hours.
Okay, good question. Now we're gonna move into some questions that are related to us here in Florida, and thinking about how our area and the Space Coast and the Lagoon might use these models. One thing that we are seeing frequently in this area is large scale developments. How would these large scale developments, including the impervious surface that comes along with them, impact the movement of water in the Indian River Lagoon system?
Yeah, totally. So I would say it depends. But like you said, if we're thinking about large scale developments, you're thinking maybe lots of buildings or parking lots where areas used to be kind of more natural. Something that you're going to lose is some of that natural habitat or ability for rain, for example, or any water coming in a different way to kind of be able to seep into the ground if it's kind of impervious. So if you don't have a good drainage system in these new developments, that might become an issue. Something with more developments that people get concerned about too is, if people are using a lot of fertilizer or other things in the yards and stuff like that. We can end up having these runoff problems. That's something else that I didn't touch on at all, but some coastal models can help you solve. So you would give kind of some information about where things start, and you can trace them and see, okay, over time, if the source is here, where did these things go? And what we would use too is some observations. I know there's some people who go out and collect water samples of different things, right? And so that would be one of the validations where we can check the results of the model and say, okay, like, are we understanding kind of where these things are coming from? So some pollution issues might become a thing, but yeah, also just not having that area be able to absorb some of the water could cause an issue. And it's always a give and take on the priorities of the area and kind of what they accept as far as their risk and making those changes. So depends.
Thanks. We have another question here. This one comes from an online user. They want to know about current models that are being used to predict sea level rise for global warming, but specifically they're curious about the accuracy of the models for predicting sea level rise in the lagoon area, and how are they actively being refined?
Okay, so again, this is like something that's related to the coastal modeling, because a lot of times we can use inputs from these various climate models, sea level rise models, where they're looking at different water levels as inputs to our model. So I personally am not as familiar with what is under the hood of those models. It's usually something similar, right? You're ingesting a bunch of data, you have it discretized in some way on some sort of grid with some sort of time scale. All of that part is kind of very similar. But I don't know the specifics, unfortunately, to be able to answer that question.
Gotcha. And then we have another question that I personally really love. Great question. And I love this question because it relates to what we do here at the Marine Resources Council. So different shoreline protections, such as traditional seawalls versus living shorelines, are you able to model to compare the effectiveness at reducing floods from these different shoreline protections?
Yeah, so that's actually a very active area of research, especially because there's a lot of interest in these natural shorelines. And we're moving away from those kind of hard protective structures because we've seen that those actually have unintended consequences that we didn't mean to happen when we put them in. And so that's actually a really active area of research where we're trying to figure out the best ways to parameterize or just come up with, numbers that describe those types of things in the model there. So for example, we were talking about the seagrass before, and we were giving it like a roughness level. So like high roughness or low roughness, and that'll slow water down or speed it up. So there's different things like that in the model that you can turn on in specific areas. So for like a hard structure, you would basically treat it like a concrete, and you would give the actual profile of the thing. For something that's more like a gray infrastructure or a nature-based solution or something like that, there's a different way that you would set that up in the model. And so some of the things that my colleagues at Deltaris in the Netherlands do is they run large scale wave simulations. So they have this huge wave tank. And what they'll do is they'll put some of those nature-based solutions in the tank itself. So they had full mangroves in there at one point, like full size. And so they're at the end of the tank, and they were simulating the waves going through and hitting the mangroves, and they had all sorts of sensors and measurement devices. And so what those experiments help us do is we try to recreate those in our models. And so we'll change different parameters and say, okay, if we're saying they're going to plant mangroves here to help reduce some of the flooding impacts, we know what numbers to kind of put in the area of the mangroves that make sense, and are based on experiments and stuff like that. So that's one way that we would take that into account. But it's a super active area of research. People are really interested in that, including myself.
Before we move into our last couple of questions, does anybody have any other cards I can come around and collect?
Answered my question. So.
Yeah.
It was good.
Sure. All right. Last of the two questions, because I myself have a question. So there have been recent resource cuts to a lot of the agencies that you mentioned, including the National Oceanic and Atmospheric Administration. There have been resource cuts to United States Geological Survey as well. How are you thinking that this may impact your ability to work and update critical models?
Yeah, so that's like a really important discussion. I mean, a lot of these different things and developments and research and data collection, all these things, they're all super interconnected. So huge funding cuts to any of these different areas kind of cause us to lag behind in some places. I will say that is kind of a shame because as the United States, like we have some of the absolute best data that you can find out there. I've tried to make models in other areas of the world and it is like you're finding these like hand-drawn maps and like all this stuff. And like we have these data sources that you can actually just go into this portal and say, here's my outline area, pull all the data from there. I want it from 1990 and I want it from 2015 and I want it from 2025. And it's like really incredible what we've been able to do with the resources that we have. It is a concern for the community, especially those of us based in the US, that if we don't continue updating all of these different things, that we're going to fall behind globally. And as like a world leader in some of these things, that's a huge shame, I think. So yeah, I would say that this is coastal modeling and understanding what's going on in our area and the atmosphere and how these things work and how they move and continuing developing that is important to you. I think that you should let people know that it's important to you. And it's important to me. So yeah. That's all I can say on that, I guess.
Yeah, that's a great answer. It's a great answer. My question too, now for those of you who don't know, I've probably talked about it enough that most of you in this room that know me know that I used to live in Charleston. So I was very familiar with the maps that she had up there in Charleston, and I use them frequently in my work to work with the city of Charleston mayor and their environmental team to come to solutions about, we've got these exact maps, this is what we're forecasting, what kind of environmental solutions can we come up with? So with that information, I just moved to this area in the last 4 months. And so I have a two-part question for you, which is, have you worked with any communities in the Indian River Lagoon area to think about some of those modeling forecasts? Or have maybe your colleagues have? And the second part of that is, Charleston's issue is deeply, I'll let you answer that question first, and then I'll move into my second question. So
yeah, awesome. Yeah, so I moved to Indy Atlantic about a year and a half ago. When I first moved here, I worked remotely as a remote employee. So when I first moved here, I had projects that were kind of already going that were in all sorts of different areas. One of my goals living here is to really learn more about what's going on in this particular area and seeing ways in which we could help bring our resources, our models, maybe teach communities like about these different models. I've gone to Florida Tech has a really amazing ocean engineering program. I know that they do a ton of research in this area, a ton of different modelings. They actually have some, they use one of our models, the Deltaris models, to do some simulations in the St. John area is one that I know about. I think they do some in the Sebastian Inlet. So that's something that I'm looking forward to continuing to kind of get to know them more and tap into. And there's a ton of amazing conservation-based groups that it's also great to get in touch with and know. So I'm looking forward to continuing to get to know people who are in the area and are working on these different topics. So personally, I have not done any projects here, but that is one of my goals coming up in the next several years, so to try to find some local things that we can contribute to.
Nice. And that is also a cue that any of y'all in the audience have contacts with local agencies, municipalities and whatnot, maybe she's someone you might want to talk to about getting some modeling for your city or town. And then the follow-up question is, of course, in Charleston, once we had all these models, the mayor released the water plan, which details a lot of different solutions that both individuals can take on their individual property to see reduced amounts of flooding, but also solutions that, you know, the cities can put in place. And so for these folks today, you have not made a water plan for the Indian River Lagoon, but what are some water plan-esque ideas that you might suggest for these folks who want to kind of think about modeling in terms of their own home and maybe what they can do to reduce some maybe stormwater runoff or reduce some flooding if
Yeah,
they're
for
seeing
sure.
that in their community?
Yeah, so I think one of the like easier things that someone could do as an individual, like I know that some organizations around here have like rain barrels that you can get. So that's actually like a water storage solution, right? So all of the water that would get collected in that, either from your gutter or however, that water would have been seeping into the ground or kind of going through the storm drain system, contributing to any sort of like runoff, stuff like that. That is a pretty simple way to not overcrowd the system, right? Like you're saving some water in your particular area. And if everyone kind of did that, then we'd have like, you know, little pockets of areas that weren't getting flooded so bad, maybe. That's just like a simple thing. I think I don't know a ton about this, but like the pollution runoff, so maybe paying attention to kind of chemicals that you're putting in your lawns and stuff like that would be something to look into just to help protect the natural part of this. So I do a lot of stuff where it's like the physics. So I don't really care a lot about the biology and those types of things. I have colleagues who that is all they do and that's all they care about. So we work hand in hand, like on these physics equations and then with the biology piece. But I know that that's really important too. And then community wise, I think it's important to kind of whenever there's these types of talks about like water plans and things like that, I think a thing that we see a lot, and I don't have any solution to this, is that sometimes people who are making the plans aren't involved in the community, and the community doesn't really know how to communicate with the people making the plans about what things are important to them. So I think as a community, being able to kind of keep an eye out for those things to make sure that your voices and opinions are heard when people are making these plans, and then working from that other side, right? The planners should be taking into account things from the community. So that's just something to think about. And, you know, if you hear that someone's doing a plan, if you're interested in it, like you should, you know, reach out and figure out what's going on.
Right. I think that's pretty sound advice. We all now have a to-do list when we go home. Thank you so much for joining us today. If we want to give one big round of applause for it. As always, if you would like to mingle, grab whatever cookies are left, get you some coffee, talk to your speaker, you are more than welcome to do so. If you are interested in joining us for our Fall in Love with Birding beginner workshop, please come see me and I will give you the link to sign up for that. Okay? Thank you guys. We'll see you next month.
Thank you.
No,